Stars like our Sun produce energy through hydrogen fusion in their cores. The overall process of hydrogen fusion converts 4 hydrogen nuclei, which are protons, into a helium nucleus with 2 protons and 2 neutrons. The process converts mass into other forms of energy because the mass of the helium produced is slightly less than the mass of the hydrogen fused. In the core of the Sun, for example, each second about 600 million tons of hydrogen fuse to make about 596 million tons of helium. The missing 4 million tons of mass become energy in accord with E equals mc squared. This energy is the source of the Sun's luminosity. The Sun and most other stars shine with remarkable steadiness because the core fusion rate self-regulates through a mechanism we call the solar thermostat, which depends on 2 kinds of balance. The first kind of balance, which we call gravitational equilibrium, is a balance between the inward pull of gravity and the outward push of pressure. These 2 forces are balanced at each point in the Sun, which keeps the Sun stable in size. The second kind of balance, called energy balance, is between the amount of energy released by fusion in the core and the amount radiated into space from the Sun's surface. This balance keeps the total thermal energy of the Sun steady. Without this balance, the interior of the Sun would heat up or cool down. Let's see how the interplay of these 2 kinds of balance acts as a self-regulating thermostat. This dial, shown at its middle position, represents the Sun's core temperature when both balances are working together to keep the temperature steady. Suppose the core temperature dropped for some reason. This would cause the fusion rate to drop because the rate of fusion is very sensitive to temperature. The core would then be slightly out of energy balance because it's making less energy than the Sun is radiating from its surface, and out of gravitational equilibrium because the lower fusion rate would cause a drop in the core pressure. Now consider this question. What will happen to the core as a result of the decrease in pressure? Will it contract and heat, contract and cool, expand and heat, or expand and cool? The answer is A. The decrease in core pressure means that the inward pull of gravity will be temporarily stronger than the outward push of pressure, causing the core to contract and heat up until both gravitational equilibrium and energy balance are restored. A slight rise in the Sun's core temperature would cause an opposite sequence of events. The higher temperature would drive the fusion rate up, which would increase the core pressure and cause the core to expand and cool until both gravitational equilibrium and energy balance were restored. This self-regulating thermostat not only explains why stars like the Sun shine so steadily, but as you'll learn later, it can also be used to understand the changes that stars undergo toward the ends of their lives when they run out of core hydrogen and the thermostat can no longer operate.